I'm going to start by saying we're all guilty. That is, people in this room plus everyone else working in the industry, or at least that's how the rest of the world sees it. They think we're responsible for the majority of CO2 emissions. But it's not that bad, but we do have a problem. Okay? Obviously, the industry does produce almost a gigaton of CO2 each year, and that's only going to climb with exponential growth. However, Sander's going to tell you about a short-term, and immediate, and local solution, which I will get to by the end of the last slide. So, most recent IATA data was published in the last few weeks, was for 2024. Since 2004, passenger numbers have increased at an average compound annual growth rate of 4.65% each year. So, starting from just below 2 billion in 2004, got to 4.5 billion in 2019, obviously the year before the COVID pandemic. At that time, the industry's fleet, passenger and freighter aircraft, consumed about 96 billion gallons of kerosene, and 92 billion in 2023, 99 billion last year, and it's forecast to use 103 billion gallons this year. That correlates to CO2 emissions of 934 megatons last year, and a projected 177 megatons, almost a gigaton this year. Now, under various agreements such as the Paris Accords and so on, the industry's CO2 emissions are allowed to peak in 10 years' time, but thereafter must decline continually for the next 15 years to 2050. The original target for 2050 was 250 to 400 megatons. So even if the industry maintains its current levels, which it won't with exponential traffic growth, we have got to slash our CO2 emissions by about 2/3, or even 70%. However, that target was changed in 21 to net zero, an even bigger challenge. Right? That's going to be a drop of whatever 977 million divided by 15 years is. That's only assuming that CO2 emissions remain level for the next 10 years, which they will not do. The larger peak of CO2 emissions that is reached by 25, and therefore the large annual reduction for each year for the next 15 years. Very, very challenging. This is basically what the industry has done since 2004. The blue line passenger numbers, I think we did in 2020, is self-explanatory. However, with each day that goes by, we replace old aircraft with new ones coming out of the factories in Washington and Toulouse and so on. And so gradually the fuel burn used per passenger does decline, which helps, but it doesn't offset the total CO2 reduction. As you can see by the two lines at the bottom, the fuel burn, the fuel actually used by the industry and CO2 emissions, they keep climbing. Just to illustrate the point of what engine manufacturers have done for us since I was a very young lad in the late 60s, early 70s. Taking 727-200 as the baseline, one generation later was in 1980, the MD-81, almost the same size. And then in 1987, we had the A320ceo, and 30 years later, the A320neo and stroke 77 MAX. And you see the fuel burn per seat there, the two latest generation.
Good afternoon, everybody, and thank you for staying for this bit of talk from my side. Some of you know me, most of you don't know me. My background is flight and fuel efficiency. So basically I've been spending the last 20 years leading up to this particular point in time. The numbers I'm going to be talking about are huge, they are mind-blowing, and I ask you to bear with me, please. If you have any questions, and I'm hoping that you will have, let's get those done during the coffee break or after. I'll be here all day. Who are we? deltaBurn. We are an R&D company. We are focused on fluid dynamics. Our IP, our patent pending IP, focuses on aerodynamic niche material. We are registered in Singapore. We have footprints in the US and in the UK. where we do STCs to bring our technology to the world. What we do is we modify fan blades of turbofan engines and we modify propellers. Our mission is to drastically lower aviation fuel burn and emissions, so direct reductions, not any replacements. And in doing so, we hope as well, because less will be needed. In doing so, we're hoping to benefit both the environment and the industry. We're trying to find the balance of the two. That's the number. 33% less fuel burn. And we can get there in the next 5 years if everything works the way we want it to work. 33% fuel burn reduction on average is the same as 33% emissions reduction. 1/3 emissions of aviation. As you know, aviation produces around 3% of the world CO2. So if we get to this point, we will have reduced the world CO2 emissions by 1%. 1/3. Wow. Let me explain. Our technology. What you're looking at is a cut of a typical turbofan engine. And what we're focusing on is that blue arrow. It's the mass flow that goes through the bypass duct. That mass flow, most of it, represents the thrust that you get out of the aircraft. So we focus on fan disk efficiency. What we do is we make the fan more efficient. And in doing so, we create a much higher flow through the bypass duct. More mass flow means more thrust and also a higher EPR. So we're using today's engines to do this. We absolutely do not touch the core. So anybody wondering if we're not doing some magic inside? No, we don't. We restrict ourselves to the fan. In fact, the core doesn't even know that something has changed. So we either get all more thrust for the same fuel burn, or if we throttle back a bit, we're back to the old thrust that the aircraft is rated for, but at a much lower fuel burn. In principle, your engines will be running in a derated fashion all the time. And just how much is what I will show you next. We also have other benefits because the engines run slower, cooler, they will live longer, time between overhauls will be extended. There's going to be a whole bunch of additional benefits. Now, is this magic? No, it's real science, and we have flight tested this. We have demonstrated this. We've done it on our own business jet. And we've done it also on a 737, and I'll show you that interesting video. The effect that we're creating is actually something like this, not with all the light and sound show, but the same effect. This is a short 1.5 minute video. It's a takeoff of a 737 with the left engine modified. start to decline. Left engine running cooler, burning less. Continuing to climb on this particular flight, I took another snapshot that you can see here. We're now at flight level 250, we're climbing. All trims are neutral. I have to mention this because somebody might just say, you have your foot in your left going to somewhere. So with the left engine modified, have a look at the numbers. First of all, you can see this throttle stagger. You see under the hand of the pilot how those two throttles are staggered. You can see the numbers, and actually I'll blow them up for you. N1 is down 8.5% on the modified engine, N2 is down almost 5%. The EGT shows 90 degrees cooler on the modified engine, and the fuel flow is down 25% on the modified engine. This is incline, this is a live flight, right? Beginning of the video, you saw some white on black text. This airplane had an issue with this left engine. The left engine was actually burning hotter and had a 5% higher fuel flow. If we correct for that, the actual EGT is down 112 degrees, and the actual fuel burn is 30% down. And this is a test flight we did with a temporary modification, not our full modification. Any questions during the coffee break, please? I also talked a little bit, or I didn't talk about it yet, but I showed you an increase in payload. Now, if you drop fuel burn by 33%, you do increase range of the aircraft by a lot. So what you're looking at here is the green line, which is the sort of normal range for an A321 with this particular engine, with those particular parameters. This is what you get from the ACAP book, from the Airbus book. If you then drop the fuel flow by a third, you can see how that range increases. Now, if you take 21 tons of payload, which is 210 passengers, then our A321 deltaBurn, modified, is actually coming very close to what an A321 long range today is doing. So that shows you the impact of what we will be able to roll out. So how are we going to do this in the industry? We will lease our STCs to the aviation industry, to the airlines, to the operators, even down to the private owner of HondaJet, as an example. We will invoice you all based on your real savings. So your data in the airline will drive the invoicing process. We have a model for that. I have lots of experience in previous activities to make that work. Also, you don't have to pay us upfront. You will actually get to pay us out of your savings. Let's just keep it nice. The product, we do the installation for you at the airline, and the installation fits inside an A-check. We also manage the camo and any maintenance that might be required. Now, the design line of our modification that we put on your fans, on your engines, is in principle C-check to C-check. However, we're going to extend that C-check a bit, so let's see what happens there. Where are we today? To do an STC for a turbofan engine aircraft is an expensive exercise. At this time, we don't have money for that. But we do have money to do a turboprop STC. And this turboprop is alive and active at the moment. We expect the first STC for the propeller to be completed by Q4 of this year. And the FAA told us that they see this modification actually as a minor alteration. This is our aircraft. It's a Merlin with the Honeywell TBE 331 engines. And at this time we have the left propeller on the right hand side. modified. And this is what we do at testing with at the moment. First, we spent a long time doing ground testing. We wanted to know exactly what the thrust was that was produced by the aircraft and the propeller engine system. Apparently nobody had really done that before. Maybe somebody had put a chain at the back of the airplane and tried to measure. What we've done is we built a real test rig, including stress sensors and everything, and we've been doing all the ground testing with that. And the next step, of course, will be the turbofan. And if we don't find the funding for that, we will just have to wait until our turboprop is producing revenues, and then we'll get there by ourselves. For the turbofan STC, we guess it's going to take around 9 months to get this in place. We plan to do around 50 STCs, all current engine aircraft combinations, and we think it will take about 5 years to get all of that done. From the turboprop, apologizing for the fact that it looks like the slides have been messed up a bit. On the left you see what the normal engine does. So the line that you see going up, it goes from ground idle to flight idle to all the way up to full power. On the left, on a normal engine, you would see a torque of around 1900 foot-pounds. On the right-hand side, you see the same test with a modified prop, and the number of torques, sorry, foot-pounds required to get to the same thrust level is only 1544. So also on a propeller, we see this effect happening. This actually is a shot taken yesterday during one of our test flights from our base in Arizona. You can see the throttle stagger. It's not really clear, but there is a bit of difference. The fuel flows are different, and the torques. The biggest difference you see are the top two small valves, which is where the ITT, the interturbine temperature difference, is really huge. You can follow us live when we're doing our test flights. You see here a screenshot of the flight radar, and I had some WhatsApp messages yesterday with the test pilots to get some real feedback, because I'm here and they're there with some numbers. This was happening at an intermediate flight level 160 with a low TAS, so the effect was not so pronounced. We see on the turbofan that the higher we fly, the faster we go, the more effect we get. This is a test cell somewhere in the UK. We had an LF507 engine in a test cell in Gloucestershire, and we ran that together with a ex-Rolls-Royce CVE in attendance, and he actually certified the numbers that he saw. Sorry that it's my face there all the time, but I just happened to be there. So. Last slide, and we're on time for coffee. Green mounting. We have talked in the past to a lot of airlines and a lot of investors about our program. Most of them think it's very interesting. Most of them have an issue with the number. They think it's too big, it's not possible, it's magic, it's a scheme. But even those companies that are always active in telling the world, how much they want to push green technology and how much they want to help the world get greener, in the end, they will not come to the table. What we need, of course, is a lot more green doing, and not so much green mouthing. In the words of our CEO, Peter Ireland, the inventor of this technology, this work will be the largest step change in aviation emissions reductions of this century. I've included the QR code here. It'll take you to my personal information page there. Our website is there as well. There's more information on our website should you want to read it. My closing message to you would be that this is not some gimmick. Given the funds, this will happen. And what we're after is that after 5 years, the entire airline fleet of the world, all 28,000, 30,000 aircraft, will be flying around the same way they do today, but just burning a third less fuel. And of course, all of that third less fuel hopefully will be SAF fuel. Thank you, Charles.
Thank you, Sander. Right, you have a question. I'm not surprised at the questions there, and I know what the answer is, but I'm going to let you answer it anyway. Major engine manufacturers like GE, Rolls-Royce invest billions annually in R&D to enhance the efficiency of their propulsion systems, as I showed in my own presentation. Why haven't they proposed these enhancements earlier?
All right, the simple and truthful answer is that all engineers that work for these OEMs have all learned from the same books, and they just haven't learned about the stuff that we have discovered. Basically, what we have discovered, once the patent is public, will basically rewrite those turbo machinery books, and then the next generation of engineers will all know what needs to be done. It's that simple, actually. They're all smart people, and we've talked to a number of OEMs already. We've talked to Rolls, we've talked to CFS. Once you take them step by step through what we've done, they get it. You see the light bulb coming on. It's actually quite simple. But yeah, that's why the major OEMs haven't really seen this yet.
Yeah, I mean, I can actually answer that as well, Sander, because I asked you the same question once, and you said back in the 70s there was something very close to making the same discovery that Peter's discovered, but we didn't have the computing power with the fluid dynamics and so on then to do it.
That's right. There's been 2,100 papers that we've studied on this subject before we did the patent, just to make sure that we were in the clear. 2 papers of those 2,100 papers came close to what we have now patented. And if only they had had the resources back then to follow through their research, they would have been there already, and we wouldn't be having this discussion at all. That's the answer.
The other thing is, I want to say, is that the picture that Sander just showed of the test cell, I was there as well in February.
Yeah, we can.
It was an ALF 502, the engine for the British Aerospace one.
The guy with the big camera, that's him.
Yeah, you can tell me I'm with a fat neck. Right. It was an ALF 502, tested in the morning. It was a regular unmodified engine, and I watched the N1 rate, the speed of the fan, and the thrust the engine was generating. It had the stressor gauged in it, measuring the thrust of the engine.
So this is Charles.
Yeah.
This is me, of course. And this gentleman here is a certified engineer. He actually certifies design work for the UK CAA, and he was there to observe this test and actually sign it off on the data. Here, of course, is the engine test cell. If you've never been to a test cell, see if you can book something, because it's nice to do. Sorry, Charles.
I was just going to say, first of all, I watched the gauges of the unmodified engine, which showed the thrust effectively. It's a sensor. And I watched the field flow, and I made notes and I recorded. I took pictures, 10 pictures of each one, right? And then a few hours later we ran the modified engine. Same thrust level, and it was a very basic modification, it wasn't the modification. Right? Hand on heart, I witnessed a 25% lower fuel burn.
Yeah. The other thing I'd like to say of that 737 test that you saw, that particular takeoff, I was one of the 3 people who actually did the modification on the fan blades themselves. We put that modification, temporary modification, in place in 38 minutes on the ramp just before departure. Right? So all we do is additive. We put this on the fan blades, and the full mod, the real stuff that you put on the fan blades, of course, is a lot more difficult to put on. But like I said, it fits within the engine. Any more questions?
Yeah. Anybody have any other questions? Because I just acted as well as the Merlin. That's in Arizona, and it is actually being flight tested now, isn't it?
Yeah.
More or less now. Yeah. And there are other sort of plans in place as well for other aircraft types. I should say engine types, actually.
So at this time, we have nothing to offer the industry. All we can tell you now is that we're doing the STC process as fast as we can. As soon as we, of course, have something to offer you, we will be in the market. And you will all be able to queue up. That's all I have to say today. Thank you very much for listening. Thank you.